unrotated strings. Okay? And in the next lecture, we'll generalize that discussion to the superstring, and then we'll continue. We'll describe the fermionics, heteronics, such things. Fine. So we started this discussion before the strings meeting. So just to remind you, what we did was to start computing the modulus partition function for the unoriented string. Okay. Now I'm going to need to come back. I'm soon going to need to add an open string sector into the unoriented string. So it's a good idea for us to remember all formulas for modulus partition functions once and for all, and then compare them. So let's do that. Okay. So I'll first remind you of the formulas for the closed string. Okay. So consider just a single free boson. Okay. The partition. What was Z tau for a single free boson? Well, this we've done many times. We know product over n, 1 over 1 minus q to the power n, 1 minus q bar to the power n, and then q bar to the power minus 1. Where q as usual is e to the power minus 2 pi tau. Q bar to the power minus 2 pi tau. With the appropriate lines. Okay, now this is just the oscillator. The product of range of this. We can do this out. Now, this is the oscillator part. We should remember we should get the zero mode part right as well. So let's do that. This is one place where the relative normalizations of the zero mode part between the closed string and the open string, your unoriented, all of that matters. We should get a relative normalization. Okay, so so let's see. So how do we do that? In order to do that, we remember that our action had 1 over 4 pi alpha, right? And then sigma went from 0 to 2 pi. We're looking at the zero mode, so that just gets rid of this 2 pi makes it 2 alpha, and we get it starts. Okay? So this is the same thing in Hamiltonian language as alpha prime p squared. In Hamiltonian system is alpha prime p squared by 2. And so the zero mode contribution is integral dp over 2 pi. This is the appropriate measure of integrating over momentum. Be 2 pi to the power dimension. Yeah? And e to the power minus alpha prime p squared by 2. Okay. Now this thing is multiplied by tau 2. The chemical potential for energy. How high? It would be tau, it would be multiplied by tau plus tau bar, or tau minus tau bar. Right? Okay, so this is the thing that we want to evaluate. And we use the fact that, this thing was multiplied by 2 pi, because our torus, the convention, this is 2 pi, and tau 2 is the height relative to 2 pi. Okay, now let's get the zero mode stuff, right? So, integral over just p squared is square root pi. Now there's a pi here that will cancel the square root pi. Okay? This 2 and 2 cancels. This pi will cancel the square root pi from the integral. So what's left is alpha prime times tau. Okay? So the answer is 1 over 2 pi times square root of alpha prime. Which Kulczynski writes as 1 over 4 pi squared alpha prime times 2 squared. Is this clear? Okay? I'm computing the partition function. The partition function is a partition function over oscillators, which we know, and partition function over 0 mode. Partition function over 0 mode is the same calculation as quantum mechanics. We just done that quantum mechanics calculation. Okay? So let me put this in. So this is equal to 1 over square root 4 pi square alpha prime dash. This is z tau for a single one. Single free boson in a circle. Okay. Now, let us also compute trace of omega times e to the power minus 2 pi t times L naught plus n. Omega, you remember from the last lecture, is the orientation reversal object. And you remember that it didn't act on 0 modes, and its action on the oscillators was to convert a left mover to a right mover. Okay? And because we didn't, in the sector where you project out by omega, we don't have left and right movers are going to be set equal. The strip that you integrate over is just a strip, it's not one dimensional, two dimensional integral. So I've made this a strip. Okay? And L naught is going to be equal to L naught bar because of this omega. So we worked out this trace last lecture, and you remember that we understood that because what omega does is change the left mover to right mover, the only sectors that contribute are sectors in which you have the same quantum numbers of the oscillators on the left mover and the right mover. Okay? So we just effectively got doubling. Here. So that as far as the oscillators went, we got product Q to the power 2 by 24, product over n, 1 over 1 minus Q to the power 2n. Where Q was equal to e to the power minus 2 by n. Okay, I could just substitute that. E to the power minus 4 pi t. 4 pi t.
The trace here is taken over the open zoom statement.
It's close to explains, but the omega projector makes left movers equal to right movers. So what partition function are we computing? We're computing this here. This is length 2 pi. This is of length 2 pi times 2 times 5. So we call that tau 2 is. This is length 2 pi tau 2. It would be a complex number 2 pi tau 2 that. And if this was here, this was there. Okay? Great. So we've got this. This object is from the oscillators. 0 mode part is totally different. So we just get exactly the same. So we get 1 over square root 4 pi squared alpha prime t. You just have to remember that in this formula, Q is equal to e to the power minus 2 pi. In this formula, in general, Q is equal to e by 2 pi I. Okay? Now, there is one more thing that we're going to do. So let's work it out how we're doing this. Let's also remind ourselves what the partition function over open strips is. Right. So there the 0 mode part is different. So let's work out the oscillator. So this is both these are closed. It's closed. That's in yellow. Closed. This is also closed. You need to visit. Now let's do it for O. Okay? And let's compute the function. Okay, so the zero norm part and the oscillators. Now the oscillators, we remember, it's just by the doubling trick. It's like for just the left movers, just the right movers. Once again, we only have to integrate over a strip. Right? So, once again, here we'll write q e to the power minus 2 pi t, and the oscillators will give us q to the power 1 by 24 minus 1 by 24. Product over n, 1 over 1 minus q to the power n. Okay, what about the zero mode part? Now, the zero mode part is different because we integrate over a length pi. So, we get 1 over 4 alpha prime times x prime. Okay? That translates in Hamiltonian language to 2 alpha prime by 2 times v square instead of alpha prime. So we have an extra 2 in the numerator, which gives us an extra factor of square root 2 in the denominator from the 0. Is this clear? So that tells us that this thing will be 1 over 8 pi squared alpha prime this is an extra factor square root 2 in the denominator compared to the closed brackets. Is this clear? Do you get my answer?
I'm just a little confused with the oscillator part because it's true that it's one of the. So this is clear for the open string. It's clear for the closed strings that QN comes from.
QN because we had we had e to the power minus 2 pi t. Right. You see, what were we computing? In the closed string situation, what were we computing? We were computing here, we were computing trace of q to the power 0, q bar to the power 0. That's what the torus partition function was. Right? Now, in our situation, q is equal to q bar. And L0 is equal to L0. So this is equal to q to the power L0 plus L0. Or q to the power 2L0. Where L0 is the L0 of the closed string.
This projection condition is basically setting them to be equal.
Setting them to be equal. That's it. You do the trace of the usual linear space.
And they're there. And
q is there, q bar. I mean, this is the thing you're computing. But you're setting them to be equal and you're setting tau to be I times t.
but in the open string case, it is altogether not there. One of the sectors is altogether not there.
Yes. In the open string case, that's right. There is only one set of oscillators.
Right.
Here the Hilbert space consists 2 sets of oscillators.
But there's a condition.
But the condition is that you sum out those states in the Hilbert space where whatever is happening to the left is also an oscillator. So that's why you double the edge. Okay, great. Now, we're going to do one last calculation of this curve, just so that you have it all on board. Now, there's one real disadvantage of this calculator. We can't use the whole board. So, we can't keep the formulas there, which is going to be big. But, okay, there are advantages. Fine. So, let's also do now. Let's also do the following. Okay? let's also look at the partition function over open unoriented strings. Okay, so what we're going to do is to look at a partition function. We'll put it all together, we'll understand why we need it. But suppose we are interested in this partition function. Over open strings, sigma goes from 0 to pi, but there's an orientation reversal operator. And this orientation reversal operator takes x of sigma to x of pi minus sigma in this case. Because the open string goes from 0 to pi. Okay? And let's try to now compute that partition. So we get trace of omega times q to the power h. Q to the power lambda. Yeah, okay, q to the power L0 from the doubling. Okay, so now we have to understand how this omega acts on the oscillators of the open string. Fine. So let's remember how the expansion for the Fourier expansion for the open string. So there are of course fancy ways of finding it, but in the simplest way, the open string, we're looking at open strings that don't enter deep range, which is 10 empty space. So they obey non-one boundary conditions at both ends. So the derivatives at both 0 and pi have to vanish. So that tells you that it's an expansion in cosines. Okay? So the expansion is in cosine n sigma, time pressed with time dependence of the oscillators. Okay? Now, under sigma goes to pi minus sigma. Cosine in sigma, well, what happens to, what is cos of pi minus sigma? Let's remember we've got the unit circle, and if you've got theta here, pi minus theta is here, so its cosine is negative. But twice of that would bring it here. So that, 2 pi. So, right, so if it was 2 pi minus 2 theta, it would be cosine of 2 theta. Okay? And then we'll alternate. Okay? So, what we're saying is that this object picks up a negative sign for odd and a positive sign for even. Okay. So we concluded that in this sector, omega alpha n omega inverse, the action of omega on these oscillators, is equal to minus 1 to the power n. Well, alpha and I was the creation of the annihilation operators for the nth state for the instance. Okay? So that tells you that what we should do is to, in this omega sector, weight the partition function so that every time you have an extra excitation of an odd oscillator number, we get an extra minus. Okay? So how do we do that? So, here we had this thing when expanded gives you states with 1 or 2 or 3 oscillators. Now, if we do the following, if we make this q to the power minus 1 by 24 square root 8 pi square alpha prime t, and then I write out the products of explicitly 1 over 1 plus q over 1 minus q squared into 1 plus q cubed. So 1 minus q to the 4 and so on. You see, this does the trick. Right? Because this when expanded gives you minus signs, has an extra -1 here. So it weights the oscillator by -q rather than q, which is what we want for all oscillators. Same for QQ. Oh, sorry, this is plus. But for Q square and Q4, it's each. Okay? And of course, the 0 watt part hasn't changed. Okay, great. So we've written down all the basic objects that we're going to do. We've written down all the basic objects we're going to need, and now we're going to process them. Is this clear? Now let's look at this object. Now, the next thing we want is to remind ourselves of modular transform, of properties of what happens to this thing as t goes to 0, to all these quantities as t goes to 0. Actually, in our analysis, we're never going to need this, except as an auxiliary trait. All of them are functions just of t, a single real number, and we're going to be interested in what happens to these objects as t goes to 0. As written, these are difficult to study as t goes to 0, because they're expanded in the series in e to the power minus t, that object goes near 1 as t goes to 0, so that many terms of the series are all concurrently follow. But the Poisson resummation, the modular transform of these objects, of course, is much easier. So as a trick for understanding this modular transformation property, what we're going okay. Now, although we worked it out in generality, with 4 pi squared alpha prime is common in all these things. And we're never going to do that. What will be important is the relative factor of square root 2. So just search one Clark formulas and then cancel. I'm going to remove the 4 pi squared alpha. Okay, everywhere. So this was square root tau 2. This was square root t. This was square root of t, and this was square root. Also, as I said, we're not interested in this lecture in the closed string partition function, except in order to get mathematical information. And the only place that we will be interested in this closed string partition function is when tau 2 is equal to I times t. So that's what we're going to look at this partition function by setting tau 2 setting tau 2 equals t. Okay? So I'm going to replace this by t here. And in that situation, q is the same as q bar. Okay? So this is q to the power 2 and this is squared, and now q is equal to 1. Now, the thing about the closed string partition function that interests me is that this object is modular. This we know. It's given by a well-defined path integral terms. Something that you could compute by latticizing, for instance. Completely well-defined. Okay? So, that tells you that this is equal to 1 over square root s q tilde 2 by 24 by product over n 1 over 1 minus q tilde to the power n over n square, where s is equal to 1 by t and q tilde is equal to e to the power minus 2 by s. Okay? Now this is some famous modular transformation property of eta function. You see? But we don't even need to know that this is an eta function. Just from the fact that that path integral is manifestly modular invariant, this is true. conclusions. We conclude in particular, okay, we'll just leave that there and use it to conclude things about each of these objects. Okay, so let's now draw a conclusion of this object. Okay, so this object here is like the square root of this in terms of the variable t prime is equal to 2. Let's define the variable t prime is equal to 2t, and let's define the variable t prime is equal to e to the power minus 2 by t prime, e to the power minus 4. Okay, so expressed in terms of q prime, or equivalent in terms of t prime, this object here is what? Okay. This object is equal to q prime to the power minus 1 by 24 product over n 1 over 1 minus q prime to the power n. Okay. But now, we had here t, not t prime. So let's write t in terms of t prime. So t is equal to t prime by 2. So we have square root 2 divided by okay, exactly. Yes. Okay? Now, is this clear? Okay, so now we're going to use this formula on this quantity. So this quantity here is the square root of this quantity almost. It's almost the square root of that quantity because we have square root of t prime here. But here, if the square root of this quantity, we would have 1/4. Okay? So, this thing is equal to, so let's define s prime is equal to 1 by t prime, and q tilde prime is equal to e to the power minus 2 by s prime. Then, we just use this formula here, which tells us that this quantity is equal to the square root of 2, and then there's a t prime to the power 1/4 times whatever we have here in terms of s prime. Okay, so then we get s prime to the power 1/4, because if we get the square root of this, that will be 1/4. Yeah? So, what we're doing is now we've taken this factor out. We have a square root of t times 2 times t prime to the power 1/4 out here. And then what remains, it should just be replaced by t prime.
But the modulus invariance is a statement about this whole quantity.
About this one.
Yeah, so we're taking a square root of that.
Taking a square root of that, and that has t to the 1.
Right.
This has a t to the half.
Okay, that would
So I'm putting out this factor, this extra factor. Okay? So then, this quantity is square root 2 divided by t prime to the 1/4 times the square root. So we should just get the square root. Square root of 2 times t to the 1/4 times square root of this. Square root of this is an x prime to the 1/4. And then there's all this q tilde stuff. Q tilde to the power minus 1 by 24 times 1 minus q tilde. Now t prime is less than by definition is 1. So this goes away. Is this clear? Okay? So I'm now going to summarize this. Okay? I'm going to write the answer. So is this correct? I'm going to drop this out and write the answer. Take your time, 10 minutes. Clear? Okay? I'm just writing the answer now. So I've got is equal to square root of 2 times e to the power. Okay, I'll continue for the q tilde prime power minus 1 by 24 times product over n 1 over 1 minus q tilde to the power prime to the power n, where q tilde prime is equal to e to the power minus 2 pi over 2t. So e to the power minus pi. Okay? Fine. Now, let's work it out for these guys.
So, thinking of this relation, you can think of like this is a set of two modular transformations that you took to reach that.
Why two modular transformations?
Like we take t here, and then we set t equals to 2t prime.
Yeah, that's
so
the way
we change t prime by t, and then we do t prime equals to 1 by
yeah. Yeah. We're just doing a variable check. I mean,
this is a modular transformation.
t equals to 2t equals to 1 by 2t is the modular transformation. Just to keep the formulas here.
So the first one is a variable check followed by modular transformation. You said that.
Exactly. Okay? Just the first thing I just did to make the formula look like this. Okay. Fine. Now let's work out the open strings. Okay. So for the open strings, once again now, we've got a formula that looks exactly like the square root of this. Okay? For the open strings, we've got a formula that looks exactly like the square root of this guy. So we do the same thing. Once again, this t comes with a square root factor rather. This time we don't have to do any variable changes. It's q, not q squared. Okay? So we just take the square root of this guy, and that very simply tells us that this is equal to 1 over the square root 2 times q tilde down minus 1 by 24 product over n 1 minus q tilde over n where q tilde equal to e to the power minus times 10 to 5 by t. Okay? And what about this guy? Unfortunately, this guy is not of this form. Okay? So, in order to tell you about how this guy modular transforms, the only way I know of doing it is by the only way I know at the moment of doing it is to appeal to theta functions. We'll leave this guy right to the end. Okay. I'll just tell you the answer at the end. About this guy, we'll worry about it. Hello? 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 Yes? Hi, I'm busy. Sorry. Okay. Fine. Okay, so far we just worked out the partition functions. We worked out the partition functions and worked out the modular transformations thereof of all the conformal field theories we need. Now, let's use this to try to understand the string theory one-loop partition functions in the presence of an oriented string. To start with just a closed oriented string. Okay, so now I'm clearing this stuff. So let's look at the string theory one-loop partition function for the closed oriented string. So, what we're supposed to do is to put 24 of these guys together. But also 2 copies of the 0 mode 2 additional copies of the 0 mode. Right? Okay, so firstly let's remember the measure. The measure for open strings was dt by 2t. It's the same for this unoriented, this Klein model. But remember that the omega comes as a projection factor, 1 plus omega by 2. Okay, so we've got really a dt by 4t. There's the half, there's an omega by 2 in there. Okay, so we'll be worrying about the contribution to the actual trace. So there's dt by 4t. And then we have now t. The factor is t. From the fact that why we have only 24 oscillators given the 0 modes in it. So So there are two x components for which we have the 0 mode integral without having the oscillators because those are cancelled out courses. So we have that 4 pi squared alpha prime t square root, but square because there are 2. We decided not to write the 4 pi squared alpha primes. Okay, so that just gives us a factor of t. Times what we have here to the power 20. Okay, so times square root 2 to the power 24 times q tilde to the power minus 1 times pi over n 1 over 1 minus q tilde prime to the power n, where q tilde prime is equal to us there e to the power minus 1. Okay. So now everything we'll be doing will have this major factor which is dt by 4. We'll have that in every integral. Right? So just to keep again formula uncluttered and remove the 4. That will be a common factor in all the. We'll be looking at the Klein bottle, the open string, the cylinder, and the Mobius strip. All three of which will have this factor of 1 over 40. That's common, so we don't need to worry about it.
But I thought that the 2 factor, I mean, the 2 in 4 is from the omega. So
from omega. So we'll be looking at from the fact that we're projecting onto onto the other way. You know, that we're projecting onto omega is equal to plus 1. But we'll be doing that in the open string sector as well. Okay, so we'll always have that off. Okay, so fine. So what we've done is this dt by d square. Now, okay, let's leave this at this for now. Let's write this as 2 right? And leave this. Before we do the next round of manipulations, let's try to calculate the same thing also for the cylinder. Okay. So if we were to do the calculation for the cylinder, once again we get dt by t times this to the power 24. But then once again we get an additional factor of, in this case, square root 2 times t. We get an additional factor in this case of square root 2 times t in the denominator. Square root 2 times square root t. So additional factor of 2 times t in the denominator from the extra 0. Right? So for the open string we get dt by 2t squared times this distance q tilde to the power minus 1 product over n 1 minus q tilde to the power n4 where q tilde is 4 is equal to power. And of course we have this additional factor of 2 to the power. Okay? Good. And we're going to have to deal with this sector a bit, the unoriented open strings, so we're postponing that. Okay. Now, the question that I'm going to ask here, is of course, why are we doing all of this? We're doing all of this because, you see, these calculations reveal a problem in the closed string theory which has unoriented closed strings. And this problem is the same problem that we saw when we were studying open strings. And it's the problem with the tag. You see, once we put this integral in this form, we can change variables of the integration to 1 over t. Exactly what we're going to change to, I'll tell you in a minute. But to some constant x 1 over t. So this becomes, let's call that number s. So it becomes ds. And then we've got these terms, which this term can be expanded in an expansion in e to the power minus s. This term here is the tachyon contribution and will have no analog in the closed string. I'm sorry, in the superstring, so we won't worry about it. But the terms that you get by expanding this quantity to the power 1. You get this q tilde to the power 1, so that cancels this q tilde to the power minus 1. That represents a closed string exchange, massless closed string exchange. As you remember from our extensive discussion of this, when we discussed theories. Okay? And so the coefficient of that term gives you a divergence because it's integral ds suppressed by nothing. Okay? We're looking at the region of small t, therefore of large s. And so s goes up to infinity, so it gives you a divergence. And that divergence, as we discussed extensively in our discussions last year, was basically the consequence of this background having a tadpole for its strings. Okay? So the key point here is that the oriented closed string, adding that into the theory at loop level and then doing loops with this object gives you an effective source for closed strings, tadpole for the massless closed strings. We'd seen this completely in discussing these open strings. Like you remember, we saw how that worked there. But the point is that the same thing happens with closed strings. Now we want to understand this statement a little diagrammatically. Okay, these two I'm clear. Right, we've dealt with and all of this. Again, we talked about this last class, but I'll just remind you. You see, this Klein model was this diagram. Right? It was this diagram where we had this, and we had this, and this was identified with this. And then what we did was we tore this up in the middle, took this out, and glued it here. So this was 0 to 2 pi and length 2 pi t. But after doing that, if you remember, as you can see from here, is we get something with length 0 to pi. Right, we get something with length 0 to pi, and this thing now is of length 2 pi times 2t. Okay? And while this quantity is just identified as usual with this quantity. What we had here was okay, and you can think of this as a cylinder with cross caps at the end being exchanged. Okay? In this picture, we think of closed string exchange between these two cross caps, and it is most usual to renormalize the length so that the closed string is length 2pi. In which case, what is this length here? Well, this length is pi divided by 2. Okay? So this length, if we think of this as being 2pi, this length is 2pi divided by 4. Okay? Okay, great. Now, the equivalent picture for the open strings, okay, was simpler. For the open strings, we just had a cylinder with exchange length, once we've done this normalization, is 2pi divided by 2. And exchange of these cylindrical lengths. Okay? So, what we learned through this calculation is that a cross cap is as much of a source for digiton tag codes. A cross cap is as much of a source for digiton tag codes as a cylinder, as the end of a cylinder is. I mean, not quite as much. I mean, it is a source for digiton tag codes, but it contributes with a relative normalization. It contributes with a relative normalization that we've carefully calculated. Okay? In order to get the last part of that relative normalization completely fixed, okay, we should re-express these two integrals in terms of the integral over S. Now, what is S? S should be the length over which the closed string propagates. Okay? That's physically what S is. So, in this case, S was 1 over 2t. But in this case, S is 1 over 4t. Okay? So, I'm going to now rewrite this integral in terms of d of 1 over 4t. Okay? So this guy picks up an additional factor, is d 4 times s. S is 1 over 40, up to minus sign of j. That is 4 times ds. Whereas this is 2 times ds.
And this factor of 2 is basically the same thing that we saw with for the closed strings. We had to do this rescaling first.
That is the same factor. Exactly. So again, we're only worrying about relative factors. But okay, let's write this as 2 into an additional factor of 2. And then we write this as 2 into 2. 2 times ds times 2 to the 13. So this was 4 times. That means 1 factor of 2 out here, 1 factor of 2 in there. And this is 2 times, so there's nothing. This 2 of course goes that. So that's ds over 2 to the 13. You see, writing it in terms of the correct S variable is very important. Because we're dealing with divergences. So, and we're comparing coefficients of divergences. So we're rescaling your integral. The term that's the constant can change by anything you want. Okay? It's very important to write in terms of this object that really is the length of propagation of the string. Why is that? It's because if you inserted momentum in here, then this divergence would be regulated in a way that would depend on that length. Okay? Because this is, you're getting divergence because you're exchanging a closed string with momentum 0. If you exchange a closed string with momentum non-zero, you would get a divergence. You get a 1 over p squared, which would tend to a divergence when the momentum is 0. So, by doing a quantity that's not actually infinite, but tends to the infinity you want, you can compare the normalization of these two things. And the right way to do it is to do that integral over the object that is the length of the channel over which the closed string propagates. Okay? So, and you remember why that is, right? I mean, if you put an e to pi p dot x here and e to pi p dot x there, then you get an additional contribution in the OPE, which is roughly e to the power, which will depend on the length separating the two operators. We discuss this again when we discuss when we were discussing the operation. So that usual discussion tells you that you see that last time we were only looking at the open strings. There's no question of what your S was. Use anything. But here comparing two different things, it's very important that the relative S's be the same. We're doing it in a diagram that's going to give us an infinity, so it's a little ambiguous. But had you take the regulated version, there would be no limit. Okay, so now that we've kept track of things very, very carefully and found that both of these terms contribute to the dipole, but with a relative factor of 2 to the 26 difference. 26, of course, the origin of that was that there were 26 dimensions. Okay. Now, the other disappointing thing is that all these things are all traces. So these things both came with a plus sign. So the signs were such that they couldn't cancel each other. So what is the logic? The logic of the story is the following. Look, we're trying to make a string theory with unoriented strings. We find that the unoriented strings give us diagrams. Okay? Now we remember that open strings also give us diagrams. So you might wonder, well, suppose you have unoriented strings and open strings. Maybe we can make it all work. Okay? But if you just had open strings and unoriented strings, open oriented strings and unoriented closed strings, that doesn't work as we see. Because both dipoles contribute to the same thing. However, you're thinking, look, it's not going to be inconsistent theory if you've got unoriented closed strings, but oriented open strings. That's not going to make any sense. Roughly speaking, you should be able to take two strings together, put them together, open strings make a closed string. If you've got open strings that are oriented, you get closed strings that are oriented. Right? So clearly the open string set has to be unoriented as well. So we're going to have another diagram. This was the cylinder. This was the Klein bottle, but in addition we're going to have this Mobius. Okay? So we should deal with that guy as well. So that's what we're going to deal with now. But any questions or comments? And the hope is that dealing with that guy can make everything work. Let's see if that works. But any questions or comments? Okay? all of you are a little puzzled. Look back on enough and you're happiest. Is there something you can articulate? Calculations of illogical.
These special factors eventually
the measure factor, like I said, if you really had, if you had operators inserted here, then you don't get infinity. Okay? You get something finite, but something finite such that it goes to infinity as the momentum inserted into those operators goes. So if you ask that this cancellation happens not just at zero momentum, but at some epsilon momentum, then it's completely unobvious. And it exists. Meaning, you see, we're asking for the cancellation of this dipole lag. But we could ask for the cancellation, some lack of bad low energy behavior if two things are exchanged between us. Okay? Asking for that is a more physical question because it gives you something really well defined. It completely fixes this measure, this right dimension.
I'm sure that when enable is obvious, there will be three factors to this whole thing.
There will be all the three factors are the same. You're talking like volume of space time.
When we do the like there are some three factors which we eventually determined by
Yeah, those are vertex operator three factors. At the moment we have no vertex operators. But suppose you do this diagram with the same vertex operators here and diagonal. Those will be universal factors. But if your worry is about something, then there's two that you have to justify. But if that's not your worry, then there's no ambiguity because one loop partition functions are a trace. And there's no ambiguity in a trace. This thing is completely, if you remember in the Josephine theory, every factor, including this thing, could be completely checked by checking that it reproduced the one loop determinant of the corresponding fields in space. A one loop determinant is a completely physical thing. It's calculating the vacuum energy. There's no ambiguity. It's a completely unambiguous one. Or if you put it at a finite temperature, will give you, number of states at which energy exists. There's no ambiguity.
Vertex operators.
But
or the vertex between
yes.
vertex operators.
Yes.
Is this the statement that the vertex operators for this open strings are there's a one-to-one map between the vertex operators for the unoriented closed strings? When you talk about open strings, the vertex operators are special and it's different from talking about all the operators.
That's a good question. Yes. You see, the vertex operators for the unoriented closed string will just be one-to-one correspondence with the states of the unoriented closed string. Okay. So now, there will be. You see, basically they're labeled by the same sets of particles. Each of them is labeled by a single oscillator. Because what's happening in the closed string sector is the same as what's happening in the closed string sector. Your occupation number at level 8.
Yeah, I was confused by the discussion that we had in the beginning. So, for the open strings, we saw that there are only one nodes. Even speaking in terms of the states, there are only one set of excitations. Let's say that left sector. But speaking in terms of unoriented closed strings, both these excitations are present. But selected number of those are. So I don't see clearly why these two should be.
Actually, let me think first. Wait. So, firstly, yeah, they're not the same thing. That's true.
So is it not? I mean, is it not possible that, like, when we talk about things where we put in vertex operators,
right,
that the factors and signs, match up such that they cancel? I mean, why? That's not possible.
No, you see, the first thing is that this thing is physical, even without vertex. Okay, I use the vertex operator kind of thing just to justify the major vertex. So once we've done that, we should just forget about the vertex operators and think of this thing by itself. Right? It really does represent a divergence coming from zero momentum close to an exchange. Okay. Now, but we haven't yet done it right because we haven't yet dealt with the fact that the open strings have to be operated. Now let's deal with that. In order to deal with that, there are two complications. The first thing is that it's a little difficult to modular transform this object. But no matter what the modular transformation is going to do, see, where did the problem come from? The problem came from that both these guys have the same sign. So either this will have no problems when you modular transform it, or it will have a problem, but it's very, very unlikely this problem could involve some other sign. But maybe it would happen, but that's not going to be the case. Okay? What we need is something with a different sign. Somehow to cancel those things. Now, you remember that when we have open strings, we have one more freedom. We can put lots of brains. We can add chant pattern factors. Okay? So let's try to do the most general thing we can. That is, look at unoriented open strings with chant pattern factors. Okay? So that's what we're going to do. So before backing out from this discussion, partition functions, we're just going to study the Hilbert space theory. So we've got some open string, and it's got some chant pattern factors, some I and J label. Some I and J label associated with this end and that end. Now we've discussed what orientation reversal does to the oscillators. But we haven't talked about what orientation reversal does to these chant pattern. Okay, so as is usual, we keep track of the championing factor state by the matrix A, whose first index tells you what's happening on the left end, and the second index tells you what's happening on the right. Okay, so now what does orientation reversal do to it? Well, it changes a string that points this way to a string that points that way. So it looks like it should interchange I and J with J and I. So it looks like it should take A to A transpose. Okay? But let's be as general as possible. So that certainly should happen. Should interchange the two ends. But it could accompany that by a similarity. The most general thing could be that the action of orientation reversal on these two ends is that times some change of basis. Change of basis in the space of Chapman. Okay, so let's make the guess that under orientation A goes to, let's call this B, A transpose B. Okay, now what can we say about this? If we change the orientation twice, we should get back to the same. Why is it the same B? Because distinction. You see, the two ends of the string have the same Hilbert space within. Right.
Let's say some star copying things you can rotate these separately, rotate these separately.
Right. But orientation change should do something on groups of deviants. And should do the same thing on every group. It shouldn't depend on, suppose you, as you said, because these brains are completely, but as you said in this picture, it's huge. Okay, suppose you have got some group here and some group here. Then the change should act, I do this orientation projection, should act in the same way as this guy, as this guy. It's just something in the field.
I mean, you can interchange the stacks.
Interchange the stacks and do something.
And do a permutation in this stack and do another permutation in this stack.
Yes, but this is an operation that is acting. Okay, that may not be what I want to say is that okay, it's a good question, but let's say, so suppose we have you see, think of it like this. Suppose you've got some Riemann surface with a bunch of holes. Now this orientation projection operator acts in some way on the boundaries of the holes. Okay? But you could have 27 of the holes. It will act in the same way on each of the holes. You see, the orientation projection operator, whatever it is, acts in some way in the bulk of the Riemann surface and somewhere in the boundary of the Riemann surface. On each boundary it has some action. But this is an action on boundaries. It won't depend on B. It won't have a different action this part of the boundary and that part of the boundary. You see what I mean? See, well, the system we have, okay, is this cylinder. No. This is, it doesn't matter. We've got the cylinder which the open strings are going around. Okay? And we're trying to understand how the orientation projection acts on this thing. So clearly the interchange is this guy now, okay? And then it could have some action on the world sheet at the edges. But whatever action it will have will be local. In the sense that it will have the same action on every boundary of the string. See, it's acting in an intrinsic way on the Hilbert space that lives on the boundaries of the string. I think that's how you should think of it. I think you should think of it this way. You see, and every boundary of the string lives in Hilbert space. This Hilbert space is n-dimensional. Okay? That pairing them together gives you the n squared different open string.
Yeah, but this super space is different.
But what we're doing is string world sheet here. So the string world sheet, any operator that's defined on the string world sheet, will act in the same way on all boundaries of the string. Okay, we could have strings that have distinct boundaries, different kinds of boundaries, but these will be different kinds of deviants. See, the open strings that we're looking at, maybe this is the right way to say it. The open strings that we're looking at begin and end in the same brains.
They make sense.
Yes.
But there is also a possibility that
No, we got these space filling. Okay, sorry. You're right. In the most general case, there was this possibility, but that's not what we're looking at. We're looking at open strings beginning and ending on n space filling brains.
all of them are going.
They fill all of space.
Oh yeah, space.
Okay? So we're looking at, we're not breaking any translational invariance. So there are n space-filling branes filling space, okay? And the orientation operator acts on these branes. So it acts on the same way as the guys ending here as on the guys ending there. It acts on the branes. Yeah, I completely agree that if you had two distinct stacks of branes, let's say 5 branes and 9 branes, let's say different dimensionalities of branes. Suppose we were looking at or 5 branes and 5 branes would separate them and so on. Okay, with say magnetic field or one. If you had things that were physically distinct, it could have distinct operations. But in this case, that's not what we said. Okay, we're looking at the situation where we've got n space-filling branes, and the open strings begin and end on the same branes. Is this clear? Okay, yeah, you're completely right on that. We could even try to invent a theory in which there are two kinds of space-filling branes. One could try funny things like that. But that's not the situation we're in. You know, what we're going to do is to try to fill all of space-time with n copies of a single brane to cancel the random. The single brane, of course, is just a D26. Or D25. Okay, good. So this is the action, but it's a good question. So this is the action that we postulate for this champion practice. Now, if you reverse the orientation and you reverse it again, you should come back to the same theory. So the action on oscillators has that property. You multiply by minus 1 to the power n, you multiply again, you come back to non-multiply by anything. So therefore the action on Chapman factors was independently held. Okay. So if I do this operation again, that is, I take V into V A transpose V inverse transpose V inverse. That should be equal to A. Okay, so that's B inverse transpose into A into B transpose B inverse has to be equal to A. Now this matrix and this matrix are inverses of each other. Right? Because if I take the inverse of this, I get B inverse on the right and B transpose here. Okay? So this is a similarity transform on A. That must give you back E. This must work for every. That's an arbitrary n cross n matrix, eh? This must be true for that. So the only way that can work is if the similarity matrix is proportional identity. Right? So B inverse transpose must be equal to A times identity. Okay? So that tells you that B must be equal to B transpose times A. But take transpose of this equation. That tells you that B transpose is equal to B times A. Plug that in here. And some number there. Constant there. Okay? Now what we're trying to do is find out what that A is. So when we get this B is equal to A squared, that tells us that A must be equal to plus minus. This equation cannot be satisfied for any constant except plus minus. Okay, so we conclude that whatever this B matrix is, okay, so we conclude that this B matrix, whatever it is, so we have this where B is equal to B transpose or B is equal to minus. for the n-dimensional vector space on the corners of, on which our chain-breaking factors act. So we can take this and make a basis change. Make a basis change on that basis. That basis change gives rise to some transformation on B that one can easily work out. Okay, you do a unitary basis change. You don't want to change your formality. You make a unitary basis change on that guy. That will give you some transformation on B that one can easily work out. Okay, and now there is this mathematical statement that that I once proved actually as a student. It was very painful to me, and I'm not going to try to inflict it here. That by such a basis change, one may always choose such a basis change to, in this case, set B is equal to identity when this is true, or to set B is equal to the symplectic matrix when that is true. So if B is equal to minus B transpose, B has to be even dimensional. This can only work on this. And when you're even dimensional, there is this particularly nice some notation is 1 minus 1 1. Let me just take it. Sorry. Where, if you remember, where he talks about, well, you may not have looked at it. Where does he talk about unoriented constraints? X, right? Within R. Okay, so claim. It's the claim is that if this B transforms in a certain way under basis changes, which you easily work out, and then this is not just a similarity transformation. It's something a little more complicated because B is a complicated transformation. It's involving the transpose. Okay, so it'll be some. In fact, don't you see how it is? It's B transforms to if B goes to U transpose B. And the claim is that under this transformation, if B is equal to B transpose, it's always possible to find a U to set B equals identity. Whereas if B is equal to minus B transpose, it's always possible to find a U to set B equals this standard symplectic matrix. Okay? I remember that when I proved it, I found that the statement, the theorem that every matrix can be written as a product of a Hermitian and a unitary part, a usual starting point. If you take the B matrix, right, it's product of a Hermitian and unitary thing, and then do a lot of blah, 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 blah. Although if 2 cross 2 matrices is very easy to know. It's very simply going to use this is true. Okay, but I'm not planning to try to do this. Okay, so I'm asking you to take on faith that there's this math, or to check for yourself that there's this mathematical statement that what you do. Okay, so this whole exercise, see, suppose we just be naive. Suppose we just be naive. What we would have said is that the Chain-Beaton factors transform like A goes to A transpose. I think a number, and I don't know the history, I'm not sure the number of people first This is information. And the only thing that we gain by not being angry is to realize that there are two possibilities. This identity is simply A goes to A transpose. Okay? But this case is A goes to symplectic matrix, A transpose, and this. So there are two possibilities. Once we chose the right basis, there are only two possible transformation laws for the gigantic factors. Okay. Now let's look at that in a little more detail. You remember that the states in the open string, the oscillator numbers n picked up a minus sign. And so if we want to keep these states, we must pair them with Chan-Payton factors that also pick up a minus sign. So oscillators numbers n when n was all picked up a minus sign. So if we want to keep these states, we must pair them with Chan-Payton factors that also pick up a minus sign under this transformation. Okay? So in particular, when n is equal to 1, so the photon is must be paired with Chan-Payton factors that pick up a minus sign. Okay? So let's look at this case first. B is identity. Okay. So in that case, we must pick up. We do get photons in our theory when n is not 1, but only for matrices that have A transpose is minus A. A is equal to minus A transpose. Because then you get a minus sign under this action that will compensate for the minus sign from the oscillators. Now what gauge group? Of course, photons are in the Lie algebra of the gauge group. So what gauge group has a Lie algebra which is made up of n cross n matrices such that A transpose is minus itself? That's XON. Okay, so in this case, we're dealing with SON. With a theory whose low energy gauge theory will involve SON bosons. On the other hand, in this case, the condition would be that B is equal to minus symplectic matrix, B transpose, symplectic matrix inverse. This defines the Lie algebra of SPA. Okay, some people call it SP2. Okay, so this is SPA. You know, there are different notations for the SPs depending on who writes them. But yeah,
It is the n cross n matrix.
Yeah, we've got SP, n cross n matrices, and I'm calling that SP. Okay, I'll remind you that the rank of this guy, is n into n minus 1 by 2. Because I believe the rank of this guy is n to n plus 1. So let's see SP.
SP2 is, I think, in this notation, it will be SU.
Is SO3. So let's check.
SU2,
SO3, and that works. Right. So that's 3. Right, 3. SP4 should be SO5. That also obviously works. And then the higher SPs are just what they are, they're not anything else. So there's nothing to check. Okay. Great. Fine. So now, just at the level of Hilbert space analysis, At the level of Hilbert space analysis, we've completed our program. Okay. So now, what we have to do in remainder is to check whether any of these N branes with either the SP gauge group or the SO gauge, whereas B being either identity or symplectic matrix, will work in cancelling a 10. Okay? So, now we have to calculate this tracing. We've done the trace over the oscillators, but we must also do the trace over the channel pattern sector. At the free level, at the level of conformal of this cylinder conformal field theory, there's no interaction between the channel pattern indices and the oscillator indices. So the trace is a product of traces. Okay? So what we need is, if we didn't have this omega factor, we would just get a product of n squared. And we just get a factor of n squared. But if we do have this omega factor, then what do we get? You see, some of the Champetian indices contribute with a +1, and some Champetian indices contribute to a -1, depending on what omega is for them. So
So it's a statement that the ladder of string states is polynomial.
what alternate?
I mean, because only the
Yes, that's the statement. N equals 1 and n equals 3 and so on will have the antisymmetric case. N equals 2, n equals 4 will have symmetric case.
because I mean, if you have a look at the master diffusion theorem, you see the case.
Right.
So
So everything will transform in some representation of SOM. But symmetric is a representation of SOM. See, just a vector is a representation of SOM. So you take two vectors and you take the antisymmetric combination of that, that's some representation of SOM. But you take two vectors and take the symmetric combination of that, that's also a representation of SOM. You see, the gauge boson expression has to transform not just